as I said, I originally was planning to go on perhaps beyond the end of the term at MIT, and so I'm happy to do so with this lecture series. And if there's continued interest, which for me is a definition of maybe 10 or above, which seems pretty likely, then we'll continue to have these. Okay, so I want to do, I wouldn't say finish, but finish what I had planned in the first pass of talking about homology of iterated loop spaces. So let's talk about some additional structure on the homology of an infold loop space. Or I'm going to use D just so that in can be used later. So these are called Kudo-Araki operations at the prime 2. And then once you make them into an algebra of operations, they've traditionally been called the Dyer-Lashof algebra. And so what are these? Well, let's get some momentum going. So let's recall how we would do the multiplication on this homology. And so what I want to do is consider if I have X in the homology of iterated loop space and Y as well, I want to consider some representing object. And if you just take the union of simplices, if this is in degree I, then this would be a union of delta I in singular homology modulo, just take any collection of two faces that restrict to the same map, as you must have to have a cycle, and then call that thing it is a pseudo manifold. So then I've got some characteristic map for this homology class X from this simplicial complex that has sort of some manifoldness to it in this canceling in pairs. And the point is that that my X is then equal to this characteristic map on what we could call the fundamental class, the top dimensional homology class of M that you get by identifying those faces pairwise. And so really it's the induced map on homology through this characteristic map. So this lets me sort of think Bordism theoretically, if you will. And then suppose I've got the same for some other homology class. Then what is the product? The product is what I get when I take M cross P and map it to omega D cross omega D, and then apply the product to that result. So this loop space has a multiplication, and so then the homology class really is, so what we would call this is this map here is maybe sigma X times Y. So the homology class looks like a product. And being a little pedantic here, but this will let us then better understand what we're doing when we want to define the Kudo-Araki operations. So next, let's also remember that there's a bracket if D is finite. And oops, move back over. So there's a bracket, and what is that? Well, I'm going to multiply in all directions. before I forget, let me remember to put on the chat in case there's any questions that come up. There we go. So what do we mean by that? Well, now I'm going to take S D minus 1 cross M cross P, and I'm going to produce a new loop for every V, and then, I don't know, call it little m, little p. And what we're going to do is, I'll draw the picture. So V is going to tell me the direction here. So that would be minus V down there. V is going to tell me the direction in which I multiply, because I'm multiplying in all possible directions. And then I'm going to apply the characteristic map on, say, the m variable here. So I've got sigma x of little m, and that's some loop. And I'm going to rescale things so that loop happens now in the disk and the boundary goes to the base point. And then I'm going to use a characteristic map for the homology class y, which is a map from P, to define the loop there. So I won't write it out in coordinates, but it's this idea of multiplying now in all of the possible directions. And that's our bracket. And so now we can define the Kudo-Araki operations. And I'm going to use lower notation because that's sort of more geometric. I'll tell you what the upper is in a second. These are denoted Qn. Here n must be less than d, which is the number of loops I am considering. And now I've got my, again, I've got my, say, m to the loop space. And I'm now going to take S n cross my m cross m. And I'm going to see that the construction will respect an S2 equivariance, and typically on the Sn, and switching the factors on the m. And that's going to, so really remember, I've got m to loops d of x, and that's going to go to this kind of construction, this new, let's call it a Reith product of m over Sn to loops dx. And so how does that go? Well, it's similar to the bracket. I've got v and m1 and m2. And then I have to remember that I'm going to think of that up to equivalence, but I'll choose a representative. And what I'll do is this element of the loop space is going to use the characteristic map of x on m1 here at v with some fixed distance, epsilon or something like that. And then at minus v, I'm going to use the characteristic map of x on m2. And if I switch the roles of v and minus v, and I switch the roles of m1 and m2, I get the same map back. So I've respected the equivalence. And so this is what you would call the operation q in x. So this would be the characteristic map for that operation q in x. So this is a way to take a homology class and produce a new one. So unlike before where we had binary operations, this is a unary operation, or just an operation, the first two being kinds of multiplication or bracket multiplication. So this goes from Qn starts takes an I-dimensional homology class and produces a 2i plus n-dimensional homology class. Okay. Great. And this is also called big Q upper I plus n, keeping track of the fact that it's raising degree by I plus n. But again, I prefer the lower notation, which I'm in a minority perhaps. So a lot of what we're going to do today, there's going to be a fair amount stated and not as much proved or even sketch proved as I'd like. One of the main statements along those lines that we're not going to touch today, but I just want to state for completeness, is that these satisfy dem relations. So these satisfy the dem relations, close cousins of those first unit operations. So if I apply Qn and then apply Qm again, so now this is a homology class in degree something like 4n plus 2m plus I, I'm going to get a sum of things where the index on the left will increase and the index on the right will decrease. And there's some binomial coefficient. And again, this should seem mysterious as to why this should be true. In fact, one of my main interests that I'm still working on, and we'll see how much I can figure out between now and a week or two when we get into some proofs, is to understand more geometrically, why would this be true? All right, so there's some pictures going on here. Well, we already had the pictures of these wreath products. So certain wreath products are homologous, and as I'll at the very least call it to attention, these it's kind of a surprising fact geometrically. There are plenty of proofs known out there, but I hope to present a little more geometric insight into them. So then let me kind of finish off our current venture into iterated loop space theory by stating a theorem of Fred Cohen, Latta, and May. They have a lecture notes in math that treats this subject, and this builds on work of Kudo-Araki, Nakaoka, etc. But they're certainly the first ones to state this as such. So and I won't even give the full statement, but if I look at the homology of iterated loops on iterated suspension, so think about n equals 1. Yes, we're working with F2 coefficients. And so that wreath product of Sn with n will have a fundamental class, right? So you have to work a bit harder to understand the P case, and again, if there's demand, I can share what I know of it, but definitely this is all over F2, and let me write that down. So over F2, because unlike, it's true that the product and the bracket were, this is with F2 coefficients. I just wrote that up above the definition of the Kudo-Araki operations. Thank you. So again, this is with F2 coefficients. Let's remember loops sigma x, you got the tensor algebra. So there's some kind of free algebra just on the homology of x as a vector space. The statement here is a free algebra with lots of structure. So we can just say free object, and I won't define fully the objects, but it's generated by the homology of x And that object means, where object means, well, of course, I have a vector space with a product, as we said, a bracket. And that product, by the way, has an antipode, because loops have inverses. And it's got a bracket, and it's degree d minus 1. And then we have the action of the Kudo-Araki operations, Qi, which satisfy the Adem relations. And then what I'm not going to specify is there's some compatibility with products and brackets and between all these structures. So we might come back to some of this, but I just wanted to state this to kind of put a wrap on iterated loop space theory. The four main parts of, or I forget whether we ended up with 3 or 4, but the main parts of the theory also sort of in the, generally you're talking about loops. Oh, and maybe I should be consistent here. So maybe this is loops d sigma dx. The opera, you have these operator actions. They give you things like products, brackets, and now these operations with finite field coefficients. And you've got your recognition principle, and that also is tied up in the operator action. And then in the case of loops on suspensions, you get free objects in a couple different senses, both geometrically and then this is the algebraic reflection. So that sort of ties up what I want to say. We might end up proving a little bit more of this later, but now let's, we will come back to that, so to speak, some of that. And after we treat homology and cohomology of symmetric groups, and it helps to actually understand the d equals infinity case first, in a sense, before some of the finite d. Okay, so let's go up in the board. To here. Okay, so so we're going to switch now to homology and cohomology of symmetric groups, but in fact, we're going to quickly see that which is something that you can state in purely algebraically. So in fact, I don't think I mentioned it. So this is on the one hand algebraic. So that's because the chains, the CW chains on our simplicial resolution of a group, they form a resolution of whatever our coefficients are over the group ring. And so that means then that then take this as a definition, if you don't already know some homological algebra, that the cohomology of BG, delta or not, they're all going to be the same, and we're going to use that fact, is just x over the group ring with trivial coefficients. And again, this is something that that you can just, it's purely algebraic. But we're going to see that it helps to think geometrically, especially with these Kudo-Araki operations. And then we're going to see on the cohomology side some different geometry. So how does that go? Well, so lemma or claim that if I take configurations of endpoints, and they're a lot of fun. Remember, the homology is this Poisson operad in R infinity. So let this dimension go to infinity. Then this is an ESN where we act on this by label permutation. So why is that? Well, so we'll get something just fairly weak. So in general, we have a fiber bundle that lets us most efficiently compute the homology and cohomology of configurations in finite dimensional Euclidean spaces. So if I take endpoints in RD and I forget one of them, it's quite easy to see that that's a fiber bundle. All the fibers are homeomorphic to, well, I'm fixing n-1 point. That means I've got 1 point left to place in RD, so it must avoid n-1 points. So it's just really taking RD and removing n-1 points. But that's homotopy equivalent to a wedge of d-1 spheres, and there'll be n-1 of those. Think about n equals 2. If I remove 2 points from a plane, I get a wedge of 2 circles, and that generalizes. And so inductively, the homotopy of configurations of endpoints in RD vanishes below in degrees less than, say, d-1. And then you were taking, what do I mean by configurations in R infinity? I'm just using the direct limit topology. And the homotopy of direct limit is the direct limit of the homotopy. And if I take the direct limit of that homotopy, I'll get 0. So again, going back to some of the things we were saying about classifying spaces, you have, for example, this wonderful simplicial construction. You might say once and for all, hey, we have a perfectly good model. Let's go on. But I hope to convince you that having this is what I would call a model coming from nature, a natural model, not in the functorial sense, but one that just sort of occurs through an object, through a space that you might define elsewhere. Remember, for example, that BON is Grassmannian, an infinite Grassmannian, and we had this cute proof of, or at least sketch of proof of Bott periodicity, mixing this two models. So here we're going to actually mostly rely on this geometric model, although we'll see, not entirely. Again, we'll mix our metaphors, we'll mix our models as we need. So let me, this is not standard, but still I prefer it to the standard things you see out there. So let unordered configurations of endpoints in X be just the quotient of configurations of endpoints in X through this labels permutation. So at the end of the day, you can think about just removing the labels, having unlabeled configurations. That's what uconf is supposed to mean. And then, one model for BSN is uconf in R infinity, or I'm going to also use uconf in of a box, an infinite dimensional box. It'll just be helpful to have bounded things, and right, we'll see in a moment. Okay. Then these spaces carry structure that are reminiscent. In fact, so these have structure much as, in fact, if you want more basic than the iterated loop spaces. So what do I mean by that? Well, iterated loop spaces have a multiplication, and these do too if I take them all together. So what I'm going to do is really think about these as the unions of, think about the union together, the disjoint union. So I'll have in components of uconf in I infinity. So remember we had our product on loop spaces. Well, there's going to be a product here. By, well, I'll just draw the picture. If I have a configuration in a box, say you have 3 points, another configuration of, I don't know, 2 points, then if I put the boxes together and rescale, again, this is very much like loop sum and a theorem that this is compatible, then I've got a configuration of 5 points. But again, this is up to, if I rescale, then I've got the same kind of configuration. So that gives a product. And then a little proposition. This is homotopic to the map which takes BSN cross BSM to BSN plus M by just sort of B delta, if we want to be clear on our models, B delta of the inclusion from Sn cross Sm to Sn plus M. If I can permute n things and m things, then I can define a permutation of n plus m things by fixing once and for all how I'm going to think of it as a union of n things and m things, and then applying those two permutations. So this really gives you a subspace, and I guess this could really be the first model. I could think of those as subspaces as well. But anyways, this is homotopy equivalent to that, and this is homotopy equivalent to that, and there's some zigzag where this stacking product and this map, which remember is just formally just taking elements of subgroups and thinking about the labels on the points on the interval. Right. So they look fairly different, but they give the same map. And I think I will, if people really want to see some proofs like that, we can take some time to do them. But let me go on. Now what we just defined were these Qj, and they're now going to go from the homology of configurations of endpoints in I infinity, unordered configurations, to, and this is all with F2 coefficients, H2I plus J of twice as many points. Let me move up. Okay. So how does that go? Well, it's pretty much the picture that I drew for you before, where if I have some pseudo-manifold, some simplicial complex whose fundamental class is the homology class I care about, mapping to this unordered configuration space. I'm going to take this kind of wreath product construction. So you have to show that you can triangulate the wreath product, use some kind of nice symmetric triangulation of the sphere so that the antipodal action is well defined. And I'm going to take n cross n and vectors, and that is going to come equipped with a map to configurations of 2 points, unordered, of course, in I infinity. And here I'll just draw the picture for you. I've got some way to, so I'm going to take V and minus V. I'm really going to think of my SI as sitting inside the R infinity or I infinity, really. And then I'm going to take my configuration of endpoints at V and the same, well, it's not always going to be the same, but the same map for configurations at minus V, with the idea that as I cross over all points in N, I'm going to get the same original, think of this as a subspace, same subspace of configurations of endpoints in each box. And notice that I have 2 endpoints here, and this is all sitting inside a box. So it's let's see, SI should be SJ. Thank you. As I said, it's not so easy to be super consistent about all of these uses. Thank you. And right, and originally n was I-dimensional. Maybe I should have said little n, but of course I had, or maybe I should use m as I did before, now that I think about it. And then I could have used lowercase m for the degree, but in any case. So let me say one thing that we'll also come back to. Again, a lot of the things in this lecture, we're gonna sort of set some ideas out and then revisit them. I claim that this corresponds to a composite of a way to produce, to take an I-dimensional homology class of BS in and first produce a 2i plus j dimensional homology class of B. And this is why we call these wreath products S2 wreath S in. And then we've got the inclusion to, sorry. What am I writing here? So this is homology. And then we've got the inclusion in homology, the map induced by homology of inclusion. In fact, it's not an injection, it's surjective with interesting kernel into the homology of BS2n. So the wreath product is, just as the product embedding of symmetric groups was important in that first product, the wreath product is important here. And as I prove some things for you, we'll definitely use this wreath product to some effect. Okay. Let me switch whiteboards. Let me make sure that I'm appropriately. So then the theorem, and again, this is a theorem now of Fred Cohen, Latta, and May. And this really is closer to, this is after, in particular, work of Nakaoka, as well as Kudo-Araki, Dyer-Lashof, etc., is that this if I take all the homology of these unordered configuration spaces, if you will, together, this is going to be, remember we have a product, it's the free algebra on this product over these operations Qj, which still have the idem relations, but now it's easier to envision a free object than in the finite loop case. And it's just generated by all of that structure by by what? Just a class in H0 of BS1, the non-zero class, the humble unit or co-unit sort of the trivial class there in homology and of BS1, the trivial symmetric group. So let me draw this out for you a bit. So, and again, we're not proving this yet. I'm trying to get all the statements and all the structure in front of us, and then we'll prove various things. So what does this look like? Well, let me give myself some room. Let's think about BS2. Now, of course, we know that that's RP infinity. So, but what we're saying is we're going to take Q1 on iota, and that's some class in the homology of BS2. And you see that what this is geometrically is sort of in the unordered configuration space of 2 points which have sort of swapped space, if you will, antipodally on a circle. And in fact, that continues. Those 2 points can be antipodally, they can range over all antipodal pairs on a 2-sphere or a 3-sphere. And in fact, instead of, let's just call Qn by abuse is Qn iota, because we get tired of writing that, we'll let context decide whether I'm implicitly applying something to iota or just taking the operation itself. So that's geometrically what the homology of BS2, and of course we know this is RP infinity, and each of these is really the fundamental class of an RPI inside of RP infinity. Okay, this already gets a lot more fun and kind of a picture that you have to draw for yourself, at least previously did in, for BS4. So remember now we have both the ring structure and then these operations. So I have things like Qi star Qj, in other words, Qi on iota star Qj of iota. And that would be, remember, this is uconf4 in I infinity. So I've got 4 points and they just orbit, say on disjoint spheres. I can have just 2 spheres. One could be at the unit, but at the origin, but one other one's away from the origin. And this would be, for example, parametrized by an RPI cross RPJ. But then we also have Qi on Qj on iota, if you will. And what does that look like? So for example, if I equals 1 and j equals 2, and by the way, I'm going to generally call these Qi comma j. So what does Q12 look like? So I've got, so Q2 means 2 points that are antipodally around, going around some 2-sphere. And Q1 says take that family. So then, and again, they don't have to be in sync or anything. So this would really be RP2 cross RP2. But then this whole thing is now antipodal around a 1-sphere. So this is represented by an S1 cross over S, the second symmetric group, RP2 cross RP2. 2. So it's some fun 5-manifold, a kind of wreath product of the sphere with an RP2. And these two kinds of classes generate the homology. In fact, the theorem is that if I restrict these to be non-decreasing sequences, so Q12 is fine, Q32 would not be kosher, then we get the full homology for just these two kinds of classes. So I've got those two kinds of classes, whereas there's just one kind of class over here. But we see the product and these operations giving us more. In BS6, so for BS6 or configurations of 6 points, I can have QI star QJ star QK. So 3 sets of 2 points dancing around each other. Or I can have QIJ star QK. So 4 points engaged in some more elaborate dance, like the one just to the left here in that picture of Q12, and then 2 other points to the side. Oops, sorry about that. And then let's then gets even more interesting, although not in an essentially different way, if we look at BS8. So there I can have QI star QJ star QK star QL, or QI star QK star QL, or QIJ star QKL. So that would be 8 points really broken up into 2 groups of 2 that are dancing around each other. But then finally, now I have something that we would call QIJK, and I'll sketch a picture of what that is maybe above. So now I've got, it's sort of a 3-nested orbital system going around some common orbit. I've got 2 systems. Each of those, if I look more closely, has 2 systems. And each of those systems consists of 2 points. So 1, 2, 3, 4, 5, 6, 7, 8 points. So that's a picture. Right. So the product is coming from that product. Andy has a question. The total homology. Well, so let's see. So first of all, I haven't said Hopf ring or Hopf rig yet. That's going to be the structure on cohomology. Right, this product does not have an inverse. So, but there's just operations. I think it's like a tensor algebra. So I think that's okay. We can just call it an algebra. We'll discuss it. Andy, you're sort of getting ahead of me a little bit on the cohomology structure as well. There's quite a bit of structure around, but right now I think it's okay that this product doesn't have inverses. It just says so this is a Hopf algebra, not a Hopf, or sorry, a bialgebra, not a Hopf algebra. That's what's going on here. That's the answer to your question, Andy. So it just doesn't have an antipode, but that's okay. So it's a bi-algebra, not a Hopf algebra. And I didn't talk about the coproduct either. So in fact, let's go there next. So the bad news, such as it is. So the good news is that this, additively, in fact, the homology of BSN with F2 coefficients, say, for all n, has been known since Nakaoka's work. And so that also means that we know the cohomology, and that's actually from, I forget whether it's 1960 or I think it's 1961. Maybe it's 1960 actually. And so we also know the cohomology because it's finite in every degree. But the cup product has been mysterious until fairly recently, until Feshbach and then my collaborators and I came along. So, the cup product, however, so this gives additive structure. This tells you what that product structure is with respect to on homology coming from the stacking of points, but we haven't told you about cup product. Well, the cup product would be a coproduct on homology, and it has a lovely formula, namely, when I've got these QJs, the diagonal and this the product map with the stacking points next to each other. Well, the stacking is a map of spaces, so this is a bi-algebra. Again, to Andy's point, not a Hopf algebra, but it's a bi-algebra. So I need to tell you what the coproduct is on the QIs, and it's what you might hope for. If these are multi-indices, then I'm just taking the sum component-wise. But let me, for emphasis, where J, K need not be admissible. And so let me give you just the first example where this comes up. The coproduct on Q22, which is this 6-dimensional class, 2 RP2s floating around and typically in S2. That coproduct is Q20 tensor Q02 plus its reverse, it's cocommutative, plus Q11 tensor Q11. And this, by an Adem relation, is Q01 tensor Q02, then plus its reverse, plus Q11 tensor Q11. So to figure out any cup products on the dual, you would constantly be applying Adem relations, and you're also working with coproducts, which are not so easy. So that's why people took a different approach using invariant theory, and I'm going to use that much more heavily in the next lecture to understand cohomology. But even there, it wasn't so easy. So here's a presentation for the cohomology of BS12, or just S12 if you understand that you're taking the classifying space. So to read this, you've got an algebra with generators in degree 1, 2, 2 in degree 3, 4, 5, 6, sorry, 2 in degree 6, and 1 in degree 7, and 1 in degree 9. And you also have generators in 5, 7, and 8. And here's your set of relations: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 relations. So what may seem fairly simple for a cup product structure from what I told you before, which remember is just this sum over j plus k equals I. If you, for example, if you're a commutative algebraist and you want to understand it in terms of generators from relations or something like that, or you're a representation theorist and you want to apply this to support varieties or something like that, or even if you're an algebraic topologist and want to understand some map and want to take advantage of ring structure, well, it seems complicated. And the reason I say seems is because we now have a sort of a different approach. So let me go up. Go up here. I go here. So let's remember that I'll just so we're so motivation that for the ordered configurations the homology was orbital and the cohomology was linear. These were submanifolds of the configuration space where point 1 and 2 had some fixed unit vector between them, and maybe points 3 and 8 had some other fixed unit vector between them, et cetera, et cetera. And they gave an interesting pairing between them. If we take the unordered configuration space, the homology is again orbital. It's a sort of symmetric orbital. I can't have, well, I have no labels on points. And really when I have things orbit each other, they themselves must be identical. I'm not allowed orbiting of things which can be distinguished. And in fact, the cohomology ends up being represented by quote unquote linear things as well. So let's just warm up by saying for BS2, that's configurations of 2 points. Our Q2 class look like this. So 2 points which are antipodal on our 2 sphere inside of R infinity or I infinity. Well, the dual to that, this is detected by the tome class, oops. The tome class of W, where W is the submanifold, or it's a little singular, but it's still where 2 points share, if this is around, say, an I sphere, share their first I coordinates. Because that will happen exactly once in this homology class when things are stacked right on top of each other. So so this is a linear condition, not just saying that the unit vector is a specified unit vector, but the unit vector lives in between these two, lives in some proper subspace. And then you can continue playing these games. So what about in BS4, if I take Q1 star Q2, that means I've got a 1 sphere and a 2 sphere. Things are antipodal around them. And I can define a subspace of configurations of unordered configurations of 4 points where I ask that my 4 points are the union of 2 points which share 1 coordinate along with 2 points, the other 2 points share, say, their 2 coordinates. So I have a union of conditions on the union of the 4 points, or union of 2 points with conditions to get some condition on 4 points. So, and then the fun thing is that the more interesting class, and I'll just draw Q1, comma 1, remember it's this thing here. And that ends up being dual to something simpler, namely 4 points which share their first coordinate again. So just like the, and why does that happen? Well, if I draw this, well then exactly once in this RP1 wreath product, RP1, RP1, do the 4 points line up. So there's the picture below. So, so this is some insight that I had in trying to extrapolate from the ordered to the unordered configurations, that somehow you can continue to define cohomology through kind of some linear conditions. And so let me try to finish up by sort of telling you what you can get from that. So there is a product from the cohomology of BSN and the cohomology of BSM, which produces a cohomology class. And again, I'm thinking of a condition on endpoints and a condition on endpoints, making a condition on n plus endpoints, sort of. I'll define it more rigorously for you next time. So by union of conditions, it is, it agrees with, it is the transfer for the map from BSN cross BSM to BSN plus M. That ends up being a covering map if you use the right model. Now, again, we'll start with some of these, nailing down some of these details next time. Well, it was first considered by Strickland and Turner, and so in fact, they found that if you take, so Neil Strickland and Paul Turner, if you take all the cohomology of BSNs together, just as the homology was this, had this algebra structure together, this, well, so it has a cut product because we're in cohomology. It's got a, this is already notation, the transfer product. And this is the coproduct. So it's dual to the product that we talked about on homology. Then they show that this forms a Hopf ring, which is remarkable. Because unlike the Hopf ring we discussed in the homology of Eilenberg-MacLane spaces, which was a Hopf ring sort of categorically, you had a ring object and you're taking homology, and so you should get a ring object. There's no sort of good ring object here. And again, I'll talk about the proof here a little bit. Similar structures agree for alternating groups and even things like GLNFP, their cohomology, but they aren't nearly as well behaved. So there's some minor miracles include about double cosets in symmetric groups that occur here from that point of view. Let me also then say recently, just to Lorenzo Guerra, Paolo Salvatore, and I show that this has a divided power operation. And that's not too mysterious. You're repeating your condition on endpoints some number of times, I times, to get a condition on n times I points, or I times n points. And the reason I say that is to, well, let's let gamma I be the following simple class, just one of these linear cohomology classes. So we're using the configuration space model, and it's going to be in degree 2 to the I minus 1 on BS 2 to the I, which again, we're thinking in terms of configurations, but let this be the tome class of all 2 to the I points share their first coordinate. Okay. And so it's the simplest thing you could, one of the simplest things you could ask for inside of configuration. It's happening in R infinity, or think of big Rn and say, okay, can I compress this configuration down to Rn minus 1? And then the theorem, and this is Chad Giusti, who is my former PhD student, Paolo Salvatore, and myself, is that if I take symmetric groups together, this is the free divided power, what we call incomponent. So there's some, if I look at this cohomology and I'm taking cup product, a lot of products are 0 because they're not, I should set them to 0 because I've got different components, different symmetric groups. So that's this incomponent condition Hopf ring on classes, on these classes gamma I. So that's it. And the claim is, and one of the first things I'll show you next time, is that this short statement implies all of these generators and relations for BS12 and all the generators and relations for any symmetric group. So we've got this Hopf ring includes cup product. So this is the natural extension of cup product structure. And within this extension, you have a very concise statement that determines the cohomology of symmetric groups with mod 2 coefficients. And again, if there's interest, we could even go further than that. Let's see. Did I lose the chat? Was there any other? Sorry, I think I might have lost my chat window. Let me double check. No further questions. So let me pause here for any questions that people are okay answering in front of YouTube, and I'll pause again after stopping the stream.
Sorry, Dev, can I just ask you to clarify? So you mean the gamma I's in all of the BSNs, or in one particular one?
No, just one particular one, because this transfer product, very good, this transfer product mixes components, so to speak.
Yeah.
Right.
So you BS2, right?
Oh. So you only need these.
Oh, I see. Right.
On BS2, BS4, BS8.
Right.
Just a single class on each 2 power symmetric group, and then we have these 2 products, and propagating those, you also need the unit classes, I should maybe say, and 1 sub n in H0 BSN. You need those unit classes as well. Interestingly enough, you throw them in somehow, or wrap them into your definition or something like that. But really all you need is 1 class from BS2, 1 class from BS4, 1 class from BS8. But now to get the rest of the cohomology of BS2, the first thing, BS4, and I'll start next lecture with this, you take this transfer product of 2 classes from BS2, and you get something on BS4. And now you're going to take cup products of what you had with some of those transfer products. And also there's this divided power operation. So you're going to take the first divided power on your BS2 cohomology as well. And that's going to give you something else on BS4. So you're wrapping things up. You have a very small number of generators, but then you have all these products that you can take.
Right.
And the relations between those products, in particular, most of the work driving these, whatever there are, 13 or 15 or whatever relations, follow from Hopf-ring distributivity. So interestingly, that one fact is kind of, you apply it again and again, and you get all of these relations. Now, what's interesting and kind of an open, and I know there's some people attending that are much more of commutative algebraists than I am. You know, what do we now maybe know about these rings now that we can present them so nicely as a Hopf ring, for example? Does this presentation help us understand the commutative algebra of these rings, which is something that actually the representation theorists use to in the theory of support varieties. So this is completely algebraic, but it's interesting that this Hopf ring structure, which for me is geometric, but Strickland and Turner found it, is kind of driving, if you want to understand spec R, where R is this ring, well, the Hopf ring structure is a better presentation and maybe can lead to some new insight in spec R, although those applications haven't been done. They're there, but I think the representation theorists have not been looking at support varieties as intently as they did about 15, 20 years ago.
Can I just ask on that point, am I right in saying that the cohomology of symmetric groups are always polynomial? Is that right?
No. Here's BS12.
These are not regular.
So do you see the projection on the screen?
You're not killing a regular sequence.
No. This is
okay. I haven't had a chance to look at them, but
yeah. Well, here's what I'm projecting now is the cohomology of BS12, and it's got this list of 10 generators and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13 relations. And God bless you if you can understand that set of relations on those 10 generators. Those
but I mean, but without actually checking, I mean, it's
these are minimal. This is
sequence.
a minimal set of relations and minimal set of generators and relations. You cannot find fewer generators and or fewer.
No, you've got some products there. Yeah, that's probably right. Yeah. No. I agree. Yeah.
I mean, there were papers back in the 90s that said this is the cohomology of BS16. Here it is, with even longer lists. And again, the claim is that all of that data is wrapped up into this statement, that the Hopf ring distributivity is really telling you what the driving all these relations, the generators and relations. And yeah, I think it would be interesting to understand that a little bit better. I mean, a Hopf ring is a ring object in a sense, so it has some commutative algebra. The components of the Hopf ring are each rings themselves, so they have some commutative algebra, and somehow the interrelationship is fairly rich. But again, I'm not that much of an algebraist, so I haven't sort of explored this further. It's one thing that I hope that maybe some folks who listen might be interested in. Other questions? It's a great one. All right, I'm going to stop the live.